Hello, this is Mr. Collier, and today we're looking at the roots of unity. So the roots of unity, and we're talking about 1. Okay, we're solving things like r cubed equals 1 or r to the power 4 equals 1. So we're looking at roots of unity, which have some special properties. And often for roots of unity, we use the notation omega to represent the roots, but we'll talk a little about that later. And here's an important factorizing that's going to come up a lot. Whenever you have any variable to the power of n minus 1, you can factorize it this way. Okay, you can factor out an omega minus 1 and then multiply by descending powers of omega. We'll get to that in a second. Find the cube roots of unity. So let's do that first. So cube roots of unity is solving the equation r to the power of n equals, r to the power 3 for cube roots equals 1. And we have 1 is here on the real axis, so the argument is 0 and the modulus is 1. So we're just solving the equation r equals cis the 0 plus 2 pi k, so we're going to have 2 pi k, and then we're going to have to the power of 1/3, which means over 3. So these are going to be, your answer is going to be in this form. And when you plug in 0, 1, and 2, you're going to get cis 0, cis 2 pi over 3, and cis 4 pi over 3. And cis 0 is just 1, so it's going to be 1, cis 2 pi over 3, and cis 4 pi over 3, which makes sense because your roots have to be evenly spaced around the axes here. Okay, so since they're evenly spaced, this should be 360 degrees divided by 3 is 120, so this angle should be 120, which is 2 pi over 3, and then you got 240, which is 4 pi over 3, right? So you can kind of shortcut it and get these answers right away. So those are the cube roots of unity. And if omega is the root with the smallest positive argument, alright, that's this one right here. This one has the smallest positive argument, because the argument of this one is 0, right? So we usually write the roots as 1 omega. You can write it as a w, that's fine. And it's a little bit hard to write omega. And this one is omega squared, because if you take this one and square it, you get this one, right? Show that the roots are this, this, and this. Well, if we let omega equal cis 2 pi over 3, that means that omega squared equals cis 2 pi over 3 squared. And by de Moivre's theorem, you can write that as cis 4 pi over 3, right? So yeah, the roots are 1 omega and omega squared, and it always works that way. If you got if you're solving for the fourth roots of unity, you're going to have 1 omega squared, 1 omega, omega squared, omega cubed, and so forth. C, very common question in IB questions. To show that this equals 0, you start with, we know that omega to the power of 3 equals 1 because it's a cube root of unity. That means that omega cubed minus 1 equals 0. And this is what we can do here. We can factorize it like this. So omega minus 1 times omega squared, and these are all pluses, so plus omega plus 1 equals 0. And we know that omega does not equal 1, right? So this thing here can't be 0, right? Therefore, this part here must be equal to 0. It's very, very common to have to do this. Show that this equals 0, you just do this. Okay, part D, draw The roots on the Argand plane, well, we already kind of did that above. The roots are always evenly spaced out. There you got 1 and 2 pi over 3. I guess right about here if I want to draw it sort of accurate. And then the other one's going to be directly down here. So notice a couple things here, like they're evenly spaced out. Also, the conjugate of omega equals omega squared. That comes up in some questions. Okay, and I guess we'll talk about some other properties like in part E. Use the sum of a geometric series to show that the sum of all the roots of unity equals 0. Yeah, so that is always the case. It kind of makes sense graphically too, because of if you think of them as vectors, they will all cancel out. So use the sum of arithmetic series. So we have this last one here should be n minus 1, I believe. But yeah, so if we look at this here, we have the r value is omega, and the first term is 1. So using the sum formula of a geometric series, the sum of the first n terms, or of n terms, is the first term times r to the power of n minus 1 over r minus 1, right? And that gives us, so this here is actually equal to 0 like we described before, right? Alright, so that's going to be 0 over omega minus 1 equals 0. So they always add up to 0. This next question, we have the cube roots of unity are 1 omega squared. Simplify this. So let's simply expand the brackets, and we get 1 plus 3 omega squared plus 3 omega plus 9 omega cubed. That should be an omega there. But recall these are cube roots of unity, so omega cubed is actually 1, and we can see that graphically too. Here are the roots of unity. There's 1, there's omega, and there's omega squared. If we do omega cubed, we just kind of like rotating another 2 pi over 3 radians. So omega cubed gets over here, and this is omega 4, omega 5, omega 6, and so forth. But it's a cube root of unity, so we know omega cubed equals 1. So this is going to be 1 plus 3w squared plus 3w plus 9 times 1, just 9, right? And there's something else we can do actually. So 9 plus 1 is 10. And let's take a look at this. Recall from number 1, we know that, and this always works out, if you add up all the roots of unity, you always get 0. So that means omega plus omega squared equals -1. So that quantity is -1, and we have 10 plus 3 times -1, which equals 7. So that whole thing just simplifies to 7.